In one of our lecture videos, we have discussed about the Doppler effect for sound waves. So at this particular lecture video, we will discuss about the Doppler effect for electromagnetic wave. So we have here a source that is moving with velocity u, and it emits waves of frequency f naught. The first wave crest is emitted here. Now take note that this source is moving and at a particular distance ut. So ut here is velocity multiplied by the time. At this particular distance, the source emits a second wave crest. Now, the position of the first wave crest at the instant that the second crest is emitted is here. Now, if Stanley is a stationary observer in the train station, he will detect waves of frequency f which is greater than f naught. So when a source moves toward the observed frequency of the observer is f, which is greater than the emitted frequency f naught. So in equation form, we have this one, f. So this is the frequency as observed in a frame of reference S, an inertial frame of reference S where Stanley is at rest, is equal to the square root of C plus U divided by C minus U multiplied by F naught. So take note here that C is the speed of the electromagnetic wave, in particular light, and U is the velocity of the train or of the source. Okay, and then when a source moves away from the observed frequency f is lesser than the emitted frequency f naught. So this will be our equation. So take note that we have f is equal to the square root of c minus u divided by c plus u multiplied by f naught. So take note of the signs of the numerator and of the denominator. So this term here, the square root of c minus u over c plus u, is always lesser compared to 1, so that f is always lesser compared to f naught. That is if the source is moving away from the observer. Alright. Now, these are particular examples. This handheld radar gun emits a radio beam of frequency f naught, which in the frame of reference of an approaching car has a higher frequency f. The reflected beam also has frequency f in the car's frame, but has an even higher frequency f prime in the police officer's frame. The application is that the radar gun calculates the car speed by comparing the frequencies of the emitted beam and the doubly Doppler shifted reflected beam. Now let us proceed to relativistic momentum. In mechanics, we have learned that momentum P is just equal to m times v. Now, to be consistent with Einstein's postulates, there has been a need to recalibrate or to re-express momentum. So here is a graph of the magnitude of the momentum of a particle of rest mass m as a function of speed v. Also shown is the Newtonian prediction P is equal to mv, which gives correct results only at speeds which are much less than c. Okay, so take a look at this graph. When we use the classical definition of momentum, which is just P is equal to mv, then we will have this graph. Now, this doesn't happen. We cannot have v which is greater than c. Now, what really happens is that um, the momentum becomes infinite as v approaches to c. So Newtonian mechanics incorrectly predicts that momentum becomes infinite only if v becomes infinite. So suppose we measure the mass of a particle to be m when it is at rest relative to us. We call m the rest mass. When such a particle has a velocity v, its relativistic momentum is given by this equation. So there is a correction. So we have P is equal to the rest mass of the particle m multiplied by the velocity of the particle divided by the square root of 1 minus v squared over c squared, where v here is the speed of the particle and c is the speed of light in vacuum. So this is the relativistic momentum, and we can write this as gamma multiplied by mv. So we have here the Lorentz factor, which relates rest frame of particle and the frame of observer. Okay, and we also have the relativistic work and kinetic energy. Now, if you can recall, kinetic energy is defined as 1/2 times mass times or v squared, the speed squared. So classical definition of kinetic energy. Kinetic energy is a scalar quantity, so we have 1/2 m multiplied by v squared. When we graph this equation, we will have this one. Okay, we will have this one, but we cannot have v which is much greater than c. So this classical definition of kinetic energy needs to be corrected. So the Newtonian mechanics incorrectly predicts that kinetic energy becomes infinite only if V becomes infinite. What really happens is that this one, as the relativistic kinetic energy becomes infinite when V approaches the speed of light. Okay, now this is the relativistic kinetic energy. So we have K is equal to mc squared divided by the square root of 1 minus v squared over c squared minus mc squared. Or we can rewrite this. We can factor out mc squared, and then we have 1 over the square root of 1 minus v squared over c squared, which is just equal to gamma. Then we have minus 1. So we have gamma minus 1 multiplied by mc squared. So here we have the Lorentz factor, which relates the rest frame of the particle and the frame of the observer. Now take note that the kinetic energy approaches infinity as the speed approaches the speed of light. So this one. If v here approaches c, so we have 1 minus c squared over c squared. That will be 1 minus 1, which is 0. And we have a square root of 0, which is 0, mc squared divided by 0, we have infinite. So we have the rest energy. We define mc squared as the rest energy. So we have gamma minus 1 multiplied by the rest energy, which is equal to mc squared. Now the total energy of a particle can be obtained by adding the kinetic energy and the rest energy. So we have, from the previous slide, we have K is equal to mc squared over the square root of 1 minus v squared over c squared minus mc squared plus this term here, mc squared, the rest energy. So we are left with this term, mc squared over the square root of 1 minus v squared over c squared, which is just equal to gamma multiplied by mc squared. Now, if we relate the total energy, rest energy, and the momentum, then we have this equation. E squared, the total energy, is equal to the rest energy squared plus P times C squared.